Up until now, everything that we've talked about, all the numbers we've talked about, have fallen under something called the real number system. However, people in engineering, or before even engineering, people realized that there were mathematical problems that resulted in real answers, but the answers didn't fall under the real number system. So we have this secondary number system called the complex number system. Up until now, if you had tried to take the square root of a negative number, your calculator would spit out an error message. It would probably say non-real answer. Some people probably did get an answer on their calculator because someone else changed the setting on it. We're going to define a complex number, I, called the imaginary number. This is going to be the square root of -1. It is part of our complex number system. So if the square root of -1 is now called I, then I squared must be equal to the real number -1. How are we going to use the imaginary unit I? I'm going to write imaginary here. Well, what if I wanted to take something like the square root of -5? Well, we're going to look at it this way. I don't normally write it like this when I solve it, but for the purposes of this example, I'm going to write it this way. -5 is -1 times 5. In Algebra 1, we learned that we could rewrite the product of numbers under a radical by separating the radical over each number. Well, we just said that the square root of -1 is I, and the square root of 5 is a decimal, so we're just going to leave it, not write it as a decimal. Do not write as a decimal. Do not write as a decimal. We're going to try to begin working in something called exact solutions, and the square root of 5 is an exact solution. Let's do a problem where we're going to rewrite a negative radical. How do you write the square root of -18 by using the imaginary unit I? Whenever you see a negative under the radical, in order to simplify the process, we're just going to write an I in front. The I in front of the radical tells you the number that was under the square root was negative. Now for now, you'll probably leave the answer like this, because we haven't reviewed simplifying radicals yet. But I am going to show you in this problem how to simplify radicals. This is something we did in algebra and geometry. To simplify the square root of 18, one way of doing it is to rewrite it as the product of two numbers. One of them needs to be a perfect square. 9 is a perfect square because the square root of 9 is 3. But you can't take the square root of 2 without getting a decimal. And in the last slide, I showed you that you can separate the radical over each number, and so we find out it's really 3 the square root of 2. And don't forget we had an I associated with this. This is how I learned it when I was in Algebra 1. You may have learned how to do this in a different way. You may have learned how to do it by using a factor tree. A square root means look for any number times itself. So any group of 2 of the same number will come out of the radical. And since there are 2 3s, we're going to take a 3 out. But I couldn't group any 2s, so the 2 stays underneath. Either way is an acceptable way of doing the problem, but this only works if the number under the radical is divisible by a perfect square, like 4, 9, 16, 25, 36, and so on. Most of the problems you'll run across right now won't be. We'll cover more of these in a future chapter. What I would like you to do now is on your own, I would like you to try simplify the square root of 12, the square root of -25, and the square root of -7. For the purpose of this unit, we're not going to discuss graphing complex numbers in the complex number plane. This is something we'll cover in pre-calculus. So in the textbook where it gives the explanation of graphing, we're not going to worry about it. It's very easy, but we're not being tested on it. It's not on any state testing. It's not on the PARCC test. We're not going to worry about it. So let's talk about what a complex number is. A complex number is any number written in the form a plus bi. A is called the real component. It's the real number part of the complex number. The bi part is called the imaginary component. So there are two components to a complex number. If a is equal to 0, and you just have bi, this is called a pure imaginary number. A pure imaginary number is just one that does not have a real component. And sometimes you're going to be giving a complex number that has a real and imaginary component, and sometimes you'll be given an imaginary number that's pure. The easiest thing to do with complex numbers is to add and subtract them. The reason it's really easy is because adding and subtracting complex numbers works like adding and subtracting any other polynomial. You just add and subtract what's called the common terms or the like terms. So in A, when I want to add 3 plus 5i to negative 2 plus 4i, these are the real component of each complex number, and I can add them. 3 plus negative 2 is 1. These are the imaginary components. 5i plus 4i is 9i, and that's the answer. Notice that I did not multiply these two parentheses together. One of the most common mistakes students make when adding and subtracting complex numbers is they try to go and distribute. Distribution is another word for multiplication. Please do not multiply these. B, real part, 4 plus negative 4 is 0. Imaginary part, negative 3i plus 3i is 0. Wait a second. What happens if you have 0 plus 0i? Well, guess what? It's just 0. These were additive inverses. Additive inverses are numbers, when you add them together, they result in 0. Subtracting, you just have to be a little bit careful about. In Algebra 1, one of the ways you may have learned to do this was to make this a plus sign and change the signs of the second parentheses. That is an acceptable way of doing it. You can go, okay, now I can go 5 and 2 is 7. And negative 3 and negative 4 is going to be negative 7i. That's not the only way of doing it. You could have also just said to yourself, all right, well, I'm going to do 5 minus negative 2. That's the real component. And then you're going to do negative 3i minus 4i because that's the imaginary component. And you still would have ended up with 7 minus 7i, or 7 plus negative 7i. Same answer. Now, the nice thing about imaginary numbers, even though they're easy, they can actually be done on your graphing calculator. I want you to notice that right above the period at the bottom of your calculator is I. That is the imaginary unit I. So if you want to type a problem into your calculator, you would use second period. So this was problem A, 3 plus 5i plus negative 2 plus 4i, and we found out the answer was 1 plus 9i. I want you to notice that when I typed it into my calculator, I kept the parentheses around each complex number, and I used I, which again was second period, and it just told me the answer. You are more than welcome to use your calculator to do the adding and subtracting. You don't have to, but you can. Now on your own, I would like you to find each sum or difference in each of these problems. Now let's talk about multiplication. Multiplication works just like multiplication did when you first learned how to multiply things that look like this in Algebra 1. You're going to distribute. Be careful when you distribute though. I'm going to get negative 15i plus 6i squared. Now at the very beginning of this lesson, we identified I as being the square root of negative 1. If you square both sides, you find out that I squared is the real number negative 1. So this becomes negative 15i plus 6 times negative 1, which is negative 15i minus 6. If you really feel the need to go back and rewrite it the other way in a plus bi form, you can write it as negative 6 minus 15i. It's the same answer. Whenever you end up with a negative 1, with an I squared, you're going to replace it with a negative 1. It's always being multiplied with the number next to it. Okay, let's go look at B. I'm going to FOIL negative 4 minus 8i, negative 3i minus 6i squared. We're going to replace the I squared with a negative 1. So negative 4 minus 11i minus 6 times negative 1. Well, this becomes positive 6. So now these real numbers are like terms, and negative 4 plus 6 is 2, minus 11i. In part C, 36 plus 6i minus 6i minus I squared. I'm going to replace this with negative 1. Watch what happens when I do that. Wait a second, what happened to the part that I just underlined? Well, 6i minus 6i is 0, so it just goes away. When I replace the I squared with negative 1, notice it says minus a negative 1, so it's going to become 36 plus 1, which is 37. When you multiply complex numbers together, it is possible that you could end up with just a real number and not a complex number. It really is a complex number. It's really 37 plus 0i, but as you know, 0 times anything is 0, and it doesn't even matter, it just kind of goes away. Now, let me show you that this is probably easier done just in your calculator. When I put problem A into my calculator, again, notice that I use the parentheses. The calculator understands this as multiplication, so you don't have to put a multiplication symbol between the parentheses. It knows that it's multiplication. Look, it gave me the negative 6 minus 15i, which is what I got when I did the problem by hand. You do not have to do the problem by hand. You can do it in the graphing calculator. That is okay. Now I would like you to try these 3 problems on your own. We've talked about adding, subtracting, and multiplying. Before we talk about dividing, which naturally comes next, we need to discuss something called a complex conjugate. The complex conjugate of a plus bi is a minus bi. A complex conjugate occurs when you change the sign in front of only the imaginary component. Now I want you, so for example, if I say, what's the complex conjugate of 5 plus 6i, you would tell me it's 5 minus 6i. If I said, what's the complex conjugate of negative 2 minus 4i, you would tell me it's negative 2 plus 4i. Notice the only thing that changes when you find the complex conjugate. When you multiply complex conjugates together, you FOIL it. The middle terms are opposite, so they cancel, and that I squared becomes a negative 1. So you're left with a squared plus b squared, which is going to be a real number. Just like when we studied radicals in Algebra 1, we don't like to have radicals in the denominator of a fraction. Now in Algebra 2, we also do not like imaginary numbers in the denominator of a fraction. So we're going to talk about how to get rid of it. All right, in order to do dividing, like 9 plus 12i divided by 3i, I'm going to multiply by something called the complex conjugate of the denominator. Remember I just said the complex conjugate of a plus bi is a minus bi. Where's the a? Well, it's a 0. So the complex conjugate of 0 plus 3i is really 0 minus 3i. So I'm going to I'm going to multiply the numerator and denominator by negative 3i. When I do that, I'm going to distribute. So I'm going to get negative 27i minus 36i squared in the numerator. And in the denominator, I'm going to get negative 9i squared. Remember that I squared is negative 1. So when each of these becomes a negative 1, the numerator ends up becoming negative 27i plus 36, because it's negative 36 times negative 1. The denominator is negative 9 times negative 1, which is positive 9. Now, I can actually do a little more simplifying of this problem. First of all, I'm going to flip the numerator. So it's 36 plus negative 27i, or it could be 36 minus 27i. And I'm going to put them both over 9. 36 divided by 9 is 4. 27 divided by 9 is 3. So it's really 4 minus 3i. All right, let's do this again. I want to multiply the numerator and denominator by the complex conjugate of only the denominator. The complex conjugate of 1 minus 4i is 1 plus 4i. Now, this is a lot of multiplying to do, and I can show you the long way. It's really just distributing. It's going to be 2 plus 8i plus 3i plus 12i squared, and that's just the numerator. Let's make that an equal sign. In the denominator, it's going to be 1 plus 4i minus 4i minus 16i squared. I'm going to combine like terms and turn that into a negative 1. So I get 2 plus 11i minus 12 in the numerator. And in the denominator, these are opposites, they cancel. This is going to become negative 1. I'm going to get 1 plus 16. Remember, this is negative 16 times negative 1, so I'm starting to skip some steps. And then the last thing I need to do is combine my real numbers in the numerator. So 2 minus 12 is negative 10 plus 11i, and 1 plus 16 is 17. So you can either write the answer like this, or you can write it as negative 10 over 17 plus 11 over 17i. This would be your real part, and this would be your imaginary part. Well, what if I wanted to do this in my calculator? Well, here's the deal with the calculator. Some people's graphing calculators will do the division for you and turn it back into a nice fraction. Some people's calculators, even though they do the division, won't turn it back into a nice fraction, and I don't know why. So I'll show you what my calculator does. I'm showing part B because it was the nicest problem to do. When I put this into my calculator, I want you to notice that I put the numerator and denominator in a set of parentheses. If you do not do that, you will not get the right answer. You must put the numerator in parentheses, and you must put the denominator in parentheses. When I first hit enter, I want you to notice that it gave me these nasty decimals. This is just the decimal equivalent of the same answer we got in class. And then I hit math enter, and my calculator changed it back into a fraction. What should you do, though, if your calculator is not turning it back into a fraction and just giving you an error message? Well, this is what I would recommend. Now I'll go back to this page. So when you got to this point in time, in order to best help you, I would just use the calculator to multiply these together. When you use the calculator to multiply the numerators together, you should get negative 10 plus 11i. And then I would use the calculator to multiply the denominators, in which case you should get 17. So then after you determine what you need to multiply the numerator and denominator by, you're really skipping to the end of the problem. Now I would like you to practice on your own and find each quotient for each of these division problems.